Welcome to video 1 for lesson 1.1. We're going to look at some terminology that we'll be using throughout the course and a quick review of some set algebra. Now when we talk about probability, we are going to be considering experiments and phenomena in which the outcome cannot be predicted with certainty. We call these random experiments. There are some obvious examples of random experiments like flipping a coin or rolling a six-sided die. But tomorrow's high temperature in Burlington can also be considered a random experiment. So can the number of surgeries performed at Fletcher Allen Hospital in a week, and the time it's going to take me to finish the Vermont City Marathon this weekend. Now, although the specific outcome of a random experiment cannot be predicted with certainty, the collection of all of the possible outcomes is known and can be described. And we call this collection of all possible outcomes the outcome space, and we denote it with S. Just as a note, many other textbooks call the outcome space the sample space. Those two terms are interchangeable, so if you hear me use the term sample space, I mean the same as outcome space. It may slip and do that because just about every other book I've ever worked with has called it a sample space, and sometimes old habits die hard. So if we're going to do that single coin flip, we know that it can either land heads or tails. So our sample space S would be the set that contains heads and tails. If we roll a six-sided die, we know that any of the numbers 1, 2, 3, 4, 5, or 6 could land face up. So our sample space is going to consist of the set with those numbers in it. The coldest it's ever been in Burlington, Vermont, I looked this up, is about negative 50 degrees Fahrenheit, and the hottest it's ever been is about 107 degrees Fahrenheit. So it's safe to say that the high temperature tomorrow should be somewhere between minus 60 degrees Fahrenheit and 115 degrees Fahrenheit. So our sample space S could be the set of all T for temperature, such that T is between negative 60 degrees Fahrenheit and 115 degrees Fahrenheit. With the number of surgeries, something that we count like this, it can take on any non-negative integer value. So our sample space S will be the set of the non-negative integers, 0, 1, 2, 3, 4, and so on. And then finally, it should take me between 3 and 4 hours to run the Vermont City Marathon this weekend, hopefully a little closer to 3 hours. So the sample space for that random experiment could be the set of all T for time, such that T is between 3 hours and 4 hours. Now often we're interested in some part of the outcome space and finding a probability of it. For instance, the probability that I will complete the marathon in less than 3.5 hours. That would be a subset of that sample space. And when we're interested in a subset of this sample space, we call that an event. So an event is just an outcome, a subset of the outcome space. If we're rolling that die, our sample space, remember, was the numbers 1, 2, 3, 4, 5, and 6. We might be interested in the event that we roll an even number. If we called that event A would be the subset of S that contains the numbers 2, 4, and 6. We might also be interested in rolling larger than a 3. If we call that event B would be the subset of the outcome space that contains the numbers 4, 5, and 6. So when we talk about an event occurring, we say that an event occurred if the outcome is contained in the event. So if we actually rolled the die and it came up with a 2 face up, then since 2 is contained in event A, we'd say that A occurred. But 2 is not contained in event B, so event B did not occur. Now since events are sets, we're often going to use set algebra when we're working with probability. So I'm going to give a brief review of some terminology and notation that we use with sets. The first is the null set. The null set is a set that contains no elements. It's also sometimes called the empty set, and that's our notation for it. A subset, if A is a subset of B, that means that all of the elements that are contained in A are also contained in B. And just as a reminder, these little diagrams, they're referred to as Venn diagrams. Kind of show us set relationships. A union B, the union of A and B, consists of all of the elements that are contained in either A or B or both. A intersect B consists of all of the elements that are contained in both A and B. The complement of an event, A, is the set that contains all of the elements in the outcome space that are not contained in A. Mutually exclusive events are events that can't occur together. It means that they have no intersection, no elements in common. Exhaustive events mean that at least one of the events has to occur. So the union of exhaustive events has to be equal to the entire outcome space. And as we see, we can have exhaustive events that intersect with each other, but if we have exhaustive events that don't intersect with each other, we call that mutually exclusive and exhaustive events. They don't intersect, cannot occur together, and exactly one of them must occur. I'm going to finish by reminding us of some important properties of set operations. First of all, the union and intersection are commutative, so A union B is equal to B union A, and A intersect B is equal to B intersect A. The associative laws also work with unions and intersections. The distributive laws are true. So A intersected with B union C is equal to A intersected with B union with A intersect C, and A union with B intersect C is equal to A union B intersected with A union C. And the last are called De Morgan's laws. This tells us that A union B complement is equal to A complement intersected with B complement, and A intersect B, if we take the complement, is equal to A complement union with B complement. And just show a couple of Venn diagrams to kind of get us thinking about why these are true. Here's the one for the first of De Morgan's laws. We can see on that top Venn diagram that A union B complement is shaded blue. In the second row, we can look at A complement shaded blue and B complement shaded blue, and we can see their intersection is the same as that A union B complement that we saw above. And the second of De Morgan's laws, if we look on the left, we see A intersect B, and then below it we see A intersect B complement, shaded green. In the right column we can see A complement and B complement, and then we can see their union, which is the same as A intersect B complement. So that brings us to the end of our first video.